So what you're seeing here on the left side is the first look at the tag SAM. So you've got the science canister, that's like the vault that protected the sample on the return journey home. And sitting inside there is the tag SAM. That's the device that actually touched the surface of Bennu, collected sample, kind of like a vacuum cleaner, except in reverse, because we were in space with no air. We brought our own air, and pushed that material inside. It's basically like an air filter. And the first thing we noticed was that there was black dust and particles all around the outer edge where the seal had laid down and protected that precious material. And the reason it got pushed out was because we had it under that nitrogen purge to keep it, the Earth's atmosphere away from it, and it pushed all the dust and particles to the edge of the canister. And I drew a little white rectangle there on the deck, and that's zoomed in on the image on the right there. And already this is scientific treasure. We see dust particles and we see millimeter particles, which are like a 1/16 of an inch or so in size. And we swept some of that material and we got it to the sample analysis, what I called my tiger team. They were here at Johnson Space Center. The electron microscopes were fired up and ready. All the other instruments were ready to go. And we got those particles in on the third day that we had the sample here in Houston on September 27th. So let's take a look at some of the first results that we got from those particles. And boy, did we really nail it. So here I'm just showing you 4 different examples. This is taken with an electron microscope. Electrons kind of behave like light waves, but they have much shorter wavelengths, so you can see very, very fine details that you would never be able to see with an optical microscope. The first panel there in the upper left, those are the water-bearing clay minerals, and they have this fibrous kind of structure. We call this serpentine because they look like serpents or snakes inside the sample. And they have water locked inside their crystal structure. And I want to stop and think about what that means. That water, that is how we think water got to the Earth. The reason that Earth is a habitable world, that we have oceans and lakes and rivers and rain, is because these clay minerals like the ones we're seeing from Bennu, landed on Earth 4 billion years ago to 4.5 billion years ago, making our world habitable. So we're seeing the way that water got incorporated into solid material and then ultimately into planets. And not just Earth, but probably Venus and Mars also had abundant water as well. The next one on the upper right, you can see the hexagon. It's got that really like stop sign kind of shape. And that's characteristic of a sulfide mineral. If we could go back, yes, thank you. And sulfur is also a critical element for planetary evolution. It determines how quickly things melt, and it's also critical for biology. A lot of the amino acids that give structure to our proteins use sulfur to link and provide those bridges. And then the bottom 2 there are iron oxide minerals called magnetite, or you might know them as a lodestone. They react to the magnetic fields. The one on the lower left is framboidal, like a raspberry, and the one on the right are plate-like. And especially those platey ones might be really important for organic evolution. They might catalyze certain reactions. So we're looking at the kinds of minerals that may have played essential roles in the origin of life on Earth. Now we can go to the next graphic. One of the coolest techniques that we have here at Johnson Space Center is X-ray computed tomography. It's like a CAT scan. So without cutting into the rock, we can actually look inside. We can see the textures and the distributions of the minerals. This helps us intelligently select areas where we want to make cuts so that we get the most exciting science results. It also gives us a good sense of the size and shape of the particle. This is the biggest one. It's about 2 millimeters across. And you can see here in red those sulfide minerals. I'm particularly fond of those. I'm an expert in sulfide mineralogy, and I can't wait to get inside and look in great detail at what's going on here. And now let's go to the last graphic. We saw Administrator Nelson show you this. I just want to point out a couple of my favorite features. Trust me, I spent the weekend staring at this image for hours and hours and getting more excited by the day. I've got 4 different focus boxes. Let's take a look at B. I call this one of the troublemakers. If you know the story of OSIRIS-REx, you know just a couple days after we collected the sample, we saw material spewing out into outer space, one of the many heart-pounding moments on this mission for me. It's because these large particles got trapped in between this flap, which was designed to keep the precious sample inside. And that's generally good news, right? Because those are big particles, and there's a lot of science to be done there. In panel C, we're just looking at some of the finer grain material, and I'm particularly interested in the different reflectance. Bennu has a salt and pepper kind of texture, bright grains and dark grains, and we're seeing that. In fact, as I was zooming around these images, I felt like I was miniaturized and running around on a tiny little Bennu. Panel D there is one of the really friable looking particles. It's got this kind of hummocky texture. It looks like the dark, large boulders that dominate the surface of the asteroid. And what gets me is the similar size or the similar shapes and textures, even as we go to these smaller sizes. Bennu seems to have this kind of fractal nature. And then finally, the last panel there, panel E, just shows two very different kinds of rocks sitting next to each other. One of our key hypotheses is that there's two major different kinds of rocks on the surface of the asteroid, darker and brighter, weaker and stronger, and we may see those already represented. And just recall, this is the material that leaked out of the tag SAM when we flipped it over. Underneath that flap, there's a whole treasure chest of extraterrestrial material, and trust me, the sample science team can't wait to get their hands on it.